Welcome to MarkScheme. Current and circuits. Everything you need made visual. Here's something that sounds impossible. Flip a switch, and the light comes on at once. The effect races down the wire near the speed of light. Yet the actual particles carrying the current, the free electrons in this copper, barely move. On average, they drift along slower than a snail, often less than a millimeter every second. So what is electric current really? And how can something so slow do so much? The answer is that current is a flow, an enormous number of tiny charges all inching along together. It doesn't matter that each one is slow. There are so many that the charge delivered every second is huge. In this video, we'll turn that picture into the equations that run every circuit you'll ever meet. Here's exactly what this covers, straight from your syllabus. IB Physics, Theme B, Subtopic 5. Electric current and the drifting charge carriers behind it. Potential difference, electromotive force, and Ohm's law. Resistance and resistivity, and the current voltage graphs for the three standard components. Electrical power in its three forms. Series and parallel combinations, tied together by Kirchhoff's two laws. And real cells with internal resistance. The good news, as always, every single part of B5 is standard and higher level common core. There is no higher level only content here. So all of it is on both the SL and the HL papers. And this one video serves both. Let's pin current down. Current, symbol I, is the amount of charge flowing past a point each second. The change in charge divided by the change in time. Its unit, the ampere, is simply 1 coulomb of charge every second. That's the whole definition, and it's in your data booklet. But we can go deeper and count the carriers themselves. Imagine a slice through a wire of cross-sectional area A. The current depends on four things. N, how many free carriers there are in each cubic meter. A, the area of the slice. V, the drift speed at which they crawl along. And Q, the charge on each one. Multiply them and you get I equals nAvq. This is why the drift speed can be tiny, yet the current large. N is astronomical. To make charge flow, you need a push, and there are two words for it. Electromotive force, or EMNF, is the energy a source, like a cell, gives to each coulomb of charge. Potential difference is the energy each coulomb gives up as it passes through a component. Both are measured in volts, and 1 volt means 1 joule of energy per coulomb of charge. Now the single most useful relationship in the topic, Ohm's law. The current through a component is proportional to the voltage across it, and the constant linking them is the resistance, so V equals IR. Resistance, measured in ohms, is just how many volts you need per amp of current. High resistance, hard to push current through. The little triangle is your friend. Cover the quantity you want, and the other two show the formula. What actually decides a wire's resistance? Three things. Wrapped in this formula, R equals R sto L over A. Rho is the resistivity, a property of the material itself, how strongly it opposes current. Then geometry. A longer wire has more resistance, because the charge has further to fight through. And a thicker wire, with a bigger area A, has less resistance, because there's more room to flow. Double the length, double R, double the area, halve R. Not everything obeys Ohm's law, and the way to tell is a current voltage graph. A pure resistor, an ohmic conductor, gives a straight line through the origin. Constant resistance. A filament lamp curves over. As current heats the filament, its resistance rises. So the line bends away from the current axis. And a diode is the odd one out. It blocks current almost entirely one way. Then suddenly conducts once the voltage passes a threshold. 3 shapes. Know all 3. Circuits do work. They heat, they light, they turn motors. So we need power. The energy delivered every second. Start simply. Power is voltage times current. That makes sense. Voltage is energy per coulomb. Current is coulombs per second. So their product is energy per second, which is power in watts. Now feed Ohm's law into it. Replace V with IR, and you get power equals I²R. Instead, replace I with V over R, and you get V squared over R. 3 phases of the same formula, all in your data booklet, and choosing the right one saves time. If a question hands you the current and the resistance, reach for I²R. If it hands you the voltage and the resistance, reach for V squared over R. Pick the form that matches what you already know. Now let's build a circuit and watch the current behave. Here's a single loop, a cell, a bulb, and an ammeter, all in series, meaning one after another on a single path. Watch the charge flow. Because there's only one path, and charge can't pile up or vanish, the same current must pass through every component. Whatever flows out of the cell flows through the bulb and back. Put a second ammeter somewhere else in the loops, and it reads exactly the same. 1.5 amps here, 1.5 amps there. That is the rule for series. The current is identical at every point. And in series, resistances simply add up, while the cell's voltage is shared out among the components. Now split the path in 2. This is a parallel circuit. The current leaves the cell, reaches a junction, and divides between 2 separate branches, each with its own resistor. The main ammeter reads 3 amps. At the junction, that 3 amps splits. Here 2 amps go down the first branch, and 1 amp down the second. And here is Kirchhoff's first law made visible. The current into a junction equals the current out of it. 2 plus 1 equals 3. Charge is conserved. Nothing is lost at the split. His second law says the voltages around any complete loop add up to the cell's EMF. Those 2 bookkeeping rules, current at junctions and voltage around loops, solve every circuit you'll be given. And note the payoff of parallel. Adding a branch gives the current a new path. So the total resistance actually drops. Let me lock in the 2 combination rules, because every network reduces to them. In series, resistances just add. The total is the sum, and the same current flows through all of them while their voltages add up. In parallel, you add the reciprocals. 1 over the total equals 1 over R1 plus 1 over R2. And here, it's the voltage that's shared, while the currents add. The consequence to remember: a parallel combination is always smaller than even its smallest branch. One last, exam favorite idea. A real cell isn't perfect. The chemicals inside it resist the current too. We model that as a small internal resistance, little r, sitting inside the cell alongside its EMF. So the EMF, the total energy per coulomb, has to push current through both the external resistor R and this internal R. Epsilon equals I times R plus R. The voltage you actually measure at the terminals is not the full EMF, It's the EMF minus the volts lost inside, I times AR. So terminal voltage equals EMF minus IR, which is just the voltage across the external resistor, IR. The bigger the current, the more voltage the cell loses internally. That's why your phone dims a little under heavy load, and why a nearly flat battery with high internal resistance sags so badly. Let's put it to work. 4 escalating examples, all my own numbers. Example 1, the warm-up. A 4 ohm resistor has 12 volts across it. Find the current, then the power. Ohm's law rearranged gives current as voltage over resistance. 12 over 4 is 3 amps. For the power, the simplest form is voltage times current. 12 times 3 is 36 watts. And just to show the forms agree, I²R gives 3 squared times 4, also 36 watts. Whichever route you take, 36 watts of heat pours out of that resistor. Example 2. A proper network. A 6 ohm resistor sits in series with a parallel pair, a 3 ohm and a 6 ohm. And the whole thing runs off a 12 volt cell. Find the total resistance, then the current the cell delivers. Always collapse the parallel part first. 1 over R parallel is 1/3 plus 1/6. Over a common denominator of 6, that's 2/6 plus 1/6, which is 3/6. Flip that over. R parallel is 2 ohms, smaller than either branch, exactly as promised. Now that 2 ohm block is in series with a 6 ohm resistor, so they simply add to 8 ohms total. Finally, Ohm's law on the whole circuit. 12 volts over 8 ohms gives 1.5 amps flowing from the cell. Collapse the parallel part, add the series part, then apply Ohm's law. That's the recipe for every network. Example 3. A potential divider. 2 resistors in series sharing out a voltage. One of the most common setups on the paper. A 4 ohm and an 8 ohm resistor sit across 9 volts. What's the voltage across the 8 ohm one? In series, the total resistance is 12 ohms, and the current, the same everywhere, is 9 over 12, which is 0.75 amps. Then the voltage across the 8 ohm resistor is that current times its resistance. 0.75 times 8 is 6 volts. Notice the shortcut, the potential divider rule. Each resistor takes a share of the voltage in proportion to its resistance. So the 8 ohm grabs 8/12 of 9 volts, straight to 6 volts. The bigger resistance always takes the bigger share. Example 4. The hardest brings in internal resistance. A cell of EMF 6 volts has an internal resistance of 0.5 ohms, and it's connected to a 2.5 ohm resistor. Find the current and the terminal PD. Start from the key equation. EMF equals I times R plus R. The EMF drives current through the external and internal resistances together. So the total resistance is 2.5 plus 0.5, which is 3 ohms. 6 volts over 3 ohms gives a current of 2 amps. Now the terminal PD, the voltage you'd actually measure across the cell, is the voltage across the external resistor, I times R. 2 times 2.5 is 5 volts. Where did their other volt go? It was lost inside the cell, I times R. 2 times 0.5. 1 volt dropped internally. 6 volts of EMF, but only 5 reached the circuit. That missing volt is the signature of internal resistance. Now the exam craft that banks the marks. 1. Kirchhoff is just bookkeeping. The current into a junction equals the current out, and the voltages around any loop add up to the EMF. Label your currents and directions before you touch algebra. 2. Series adds resistances directly, but parallel adds reciprocals. So in a mixed network, collapse the parallel groups first, then add the series parts. 3. When a cell has internal resistance, its terminal voltage drops below the EMF. And the more current you draw, the bigger that drop. Watch for it whenever a question mentions internal resistance or a real battery. 4. Choose the power formula that matches what you're given, so you don't waste a step finding a quantity you don't need. And 5. The one that saves the most panic. The circuit symbols and all of these equations are printed in your data booklet. So find them, quote them, and substitute. Finally, the 4 traps that quietly cost marks. 1. Adding parallel resistances straight up. 3 ohms and 6 ohms in parallel is not 9 ohms. You add the reciprocals and flip, giving 2 ohms. 2. Forgetting internal resistance. If a cell has an R, use EMF equals I times R plus R, not plain IR, or your current comes out too big. 3. Mixing up the rules. In series, the current is the same. In parallel, the voltage is the same. Swap them and everything unravels. And 4. Grabbing the wrong power formula. Match it to the quantities you were given. Dodge these 4, and B5 becomes reliable marks. And that is B5, current and circuits, fully covered. Current as charge per second, and the slow drift of the carriers, potential difference, and EMF, Ohm's law, resistance, and resistivity. The VI graphs for ohmic conductors, filament lamps and diodes, power in 3 forms, series and parallel combinations, with Kirchhoff's 2 laws, and the real cell's internal resistance pulling down its terminal voltage. Every part of it sits on both the standard and higher level papers. That also completes our first foundational batch. Next, the IB Physics core continues. For more, that's markscheme.app. See you there.